Hey there, calc folks. Back here with another video for you in my, well, really the last video for, well, no, not quite last topic, I should say. I do have two more videos I want to put together for you here. This being one of those, where we're looking at, well, first of all, multivariable functions, but specifically focusing in on the case for differentiation and the case for partial differentiation, folks. So that is where we're at in our lecture, right? Is we are looking at some application of our partial derivatives, and we're really there at the last topic for this semester. We are going to move on and now consider the case for integration in the next chapter. So we're wrapping up our study on those partials, and the last topic we have to look at is extreme values. Yeah, using partial derivatives to calculate extreme values for multivariable surfaces. Right. There is a process we're going to consider, right? And it's going to be very analogous to what we saw back in Calc 1 when we were looking at extreme values. We had a case for looking at extreme values on open regions, and we were looking at a case for extreme values on closed regions. In the case of open regions, we could find local extreme values using some methods, right, presented using some derivative tests, and we're going to see a derivative test presented here. And then we can calculate absolute extreme values on closed intervals, folks. We consider that second case. Applying, what is that? I believe it's called the extreme value theorem, right? And the guarantee of maxes and mins, absolute maxes and mins. Using that guarantee to give us a methodology to find a solution. All right. So we're going to look at those two methods here, folks. You can see where I do begin is I do begin by looking at the local extreme values of multivariable functions, and maybe I should be more specific there. The local extreme values of multivariable functions on open regions in, well, we'll just say on open regions. All right. Local extreme values of, and you're right, these functions that have more than one variable. We are going to be looking at just strictly f of x comma y, right, in our approach here. So we are not going to be looking at hypersurfaces and their extreme values. All right. Although we would see very analogous technique folks develop. But where it all begins for us, folks, is looking at finding critical points. Both of our techniques are going to require us to analyze a function for its critical values. And how we analyze a multivariable function z equal to f of x comma y for its its critical values, right? For its multivariable critical values, right? We're going to look at its first partials, right? Its critical values are going to happen either where the first partials of our function equal 0 simultaneously, which is what's highlighted by this equation here. F's first partial with respect is going to have to equal 0. F's first partial with respect to y is going to have to equal 0. And then likewise, they're both going to have to equal 0 simultaneously. Right? That's what this statement is saying. Or where one of the two partials does not exist. That's where we would also find critical points. All right, folks? Those two conditions are going to set us up for finding our critical points, right? Typically, we're going to be looking at where our first partials equal 0 simultaneously. Right? However, there are going to be some instances where we're going to have to watch out for where our first partials don't exist. And those will also become points we want to test as critical points. All right? Not every critical point is an extreme value. We do have to test them, folks. And if you remember back in Calc 1, over open regions, we had a derivative test, and we're going to see a second derivative test develop here. But if we consider just finding critical points, right, I do consider finding the critical points of this multivariable function seen here, right? Where in this case, to find our critical points, we are going to look at our first partials and consider where do they equal 0. And what we might notice is in this first case, f's first partial with respect to x, right, will produce 2x minus y plus 2. And when does that equal 0, right? Well, that's when y equals 2x plus 2, which is a line with a slope of 2 and a y-intercept of 2. And we might consider when does the first partial of f with respect to y equal 0. Well, in this case, the first partial of f with respect to y, right, we'll go through and take its first partial with respect to just the terms involving y, treating everything else as a constant, and you would produce 2y minus x minus 2 in value. And when does that equal 0? Well, if we solve it for y to get a nice linear description of that, that's going to be when y equals 1/2 x plus 1 in value. Solving that partial set equal to 0 for y yields this result for y. So this is where our first partial of f with respect to x equals 0, is along that line. And this is where our first partial of f with respect to y equals 0 along this line. So where do they equal 0 simultaneously is where these two lines intersect in the xy coordinate space. Where this line intersects that line is where we're going to expect these two partials to equal 0 simultaneously. That is where we will satisfy this condition. They will equal 0 and equal each other at the same time at that location, known as a critical point. Right? So with these two equations, to figure out where do they equal each other in two-dimensional space without actually sketching their graphs, well, we can set these values of y equal to each other. Setting 2x plus 2 equal to 1/2 x plus 1. Right. And solving for x, we do find that x would be equal to negative 2/3 in value. And thus, if we take that negative 2/3 and substitute it into either of these two equations for y, negative 2/3 in for this x, negative 2/3 in for that x, either case, you will obtain your y coordinate in that critical point, which would be 1/3 in value. Thus, our critical point on this surface f occurs at negative 2/3, 1/3 in value. Right? That is finding critical points, folks. In this case, and in most cases, you're looking for when do your first partials equal 0 simultaneously. And what you do is you look for when do they both equal 0 on their own, develop that description, right? This is the partial, when the partial of f with respect to x equals 0. This is when the partial of f with respect to y equals 0. And what you become interested in is when do they equal 0 simultaneously. And that is where they are overlapping in the xy coordinate space, where they intersect each other, right, at these locations, right, individually. In this case, they intersect each other at, what was it, negative 2/3, 1/3 in value. And that is what becomes our critical point. Right? You can actually test that point. If you were to plug that point back into both these partials, it would equal 0. Right? This is a point that exists on both of these lines. So it's the critical point that satisfies this condition. Right? As for when these partials don't exist, right? Notice this is a linear equation. It exists everywhere. There's no concern there. This partial, it exists everywhere. There's no concern there. If we had a logarithm or a rational or a radical, there is potential that we might not exist, and we got to watch out for that. But we don't in this case. No worries. Right? No worries for critical points for non-existence. All right. Now, as noted, how do we test critical points in this case? In the case of looking at local extreme values on open regions, we can test critical points using the second partials test. To determine if a critical point is a location of a local maximum, minimum, or what's known as a saddle point in some open region. All right. Now, here is the second partials test. Well, first of all, we take note what a saddle point is, because this is kind of new to us. I think we all can imagine what a local max would look like. That's like the top of a hill. And a local minimum would look like the bottom of a hill. If we thought about a circular or an elliptical paraboloid that opens either down or up, those would have local maxes or mins on their tops or bottoms, right? But what's a saddle point? A saddle point is what I have illustrated here. It's where the two partials of f with respect to x and y, two first partials of f with respect to x and y, do equal 0 simultaneously, but their concavity does not form in the same direction, right? In one case, the concavity forms up, and in the second case, it forms down. All right, folks. All right. Hey there, folks. Sorry, I'm back. I went off to see if I could find if I had this in Mathematica, this illustration, so I could rotate it around for you, and I don't. When I was jumping back in here, I got called off to dinner, so I went and ate some dinner. I'm back now. Let me continue here. We were defining concavity, right? It is where, if we notice in this shape, we would have the slopes of the lines tangent to our, well, should be careful there with that, all that tangency stuff. The first partials would be equal to 0 at this location, but the concavity happens in opposite directions. Here we might say this curve is concave up in this direction, whereas the curve here is concave down in this direction. And what it creates is this saddle point shape, folks. It is where you could potentially have a critical point, but it's a critical point known as a saddle point. It's not an extreme value. All right, take note. And the second derivative test does help to identify all these items, extreme values and saddle points. Now here's the second derivative test. Right? It says, suppose the second partial derivatives of f exist at a critical point a comma b, where those first partials with respect to x and y at a comma b both equal 0 and each other simultaneously. Right? Letting dx comma y be the calculation seen here made with the second partial derivatives of f and the mixed partial, right? Letting d of x comma y be what we call the discriminant of the test. It's going to be a value that we calculate to help us determine behavior, right? It helps us to determine whether or not we actually have a case for local max, a local min, saddle point, or what we might call a inconclusive test. All right. You will notice that there are 4 results to the test that do, first of all, depend upon what is the value of the discriminant at our critical point a comma b, and what would be the value in some cases with respect to our second derivative of f, second partial derivative of f at a comma b. All right. If the discriminant is greater than 0 at a comma b, in either case 1 or 2, those are the cases for local extreme values, right? If your second partial, either with respect to x, and this is also true with respect to y at a comma b is less than 0, you have what we call a local maximum at a comma b. You'll be describing concave down in that sense, right? If the second derivative is less than 0, so that would relate to a maximum value, a local maximum. Whereas if you calculate the discriminant and it's greater than 0, and your second partial at a comma b, either with respect to x or y, here the derivative test sets itself up with respect to x. If that's greater than 0, you have concave up, and you would expect to have a local minimum at that location, at that critical point. If you calculate that discriminant and it's less than 0, you have the case for a saddle point. Then that will be a saddle point at a comma b. And the one case that we haven't considered is if it equals 0. If it equals 0, then you have the case for an inconclusive test. And you have to maybe go back and look at some other ways of looking at extreme values. You may have to sketch the level curves or look at behavior of it graphically in some manner, all right, to determine extreme value. All right, if it has one, or if it's a saddle point, or what's going on there at that critical point, right, respectively. That's the second partial test. Once you identify your critical points, you're going to have to formulate your what we call discriminant, this function d of x comma y, using your second partials of your function. Evaluate the discriminant at a comma b, which first of all gives you what direction you're going to head into result 1, 2, or 3, or 4. And then depending upon which case you're in 1, 2, 3, or 4, if you're in case 1 or 2, you're going to go back and look at your second partial with respect to x or y at a comma b. And if it's less than 0, you have a local max, and if it's greater than 0, you would have a local min. That's second partial. It's value. If it's greater than 0 or less than 0, you would have these cases. All right, let's look at an example. We do consider again what I opened with. We do know that this has a critical point at that location, negative 2/3, comma 1/3. We do know its first partials are seen as these values here. And if we go on to find our second partials and our mixed partial, we would note our second partials and our mixed partials would be given by these values seen here. They're all constants conveniently. They don't always turn into constants, folks, but here conveniently they are constants, which means if we calculate our discriminant with these, if we consider what would be the discriminant function, that would imply that the discriminant function is the constant value of just 3, right? This partial times this partial minus this partial squared. That will be 4 minus 1, which does equal 3 in value. It does have that implication. Since that discriminant is greater than 0, we have either case 1 or 2 occurring. Now to determine which case it is, we look at what is happening at the second partial with respect to x. Or with respect to y, both of them yield the same value. That since it's constant again, both of those are greater than 0. So that would be this particular case. Since the discriminant is greater than 0 and the second partial is greater than 0 at that critical point, then there must be a local minimum at that critical point. And that is what we end up confirming here. Right? Since that discriminant is equal to 3 and greater than 0 at that critical point, and the second partial at that critical point equals 2 and is greater than 0, there must exist a local minimum value at that critical point. And the local minimum value of the function would be f at negative 2/3, comma 1/3, which would be negative 2/9 in value. And we can actually see that illustration here of our surface. This is our surface, and here is our critical point happening at negative 2/3 with respect to x, positive 1/3 with respect to y, and it's occurring at a height of negative 2/9 on the z-axis. And it's highlighting that point on our surface, folks. That would be the local minimum value found on this surface. Right? That is the point illustrated by negative 2/3, 1/3 in the domain, and negative 2/9 in the range. All right. Folks, that is local extreme values on open intervals, right? Open regions, and critical points. Right? Both of these processes will begin by finding your critical points, which are defined as above, either where your first partials, well, equal 0 and each other simultaneously, or where either one of those may not exist will be where your critical points occur. And then once you have your critical points, you can test them in the second partials test. Calculate your second partials, formulate your discriminant, evaluate your discriminant at those critical points. If your discriminant's greater than 0, you have a local extreme value. If your discriminant's less than 0, you have a saddle point. And if equals 0, the test is inconclusive. If the discriminant is greater than 0, and you have a local extreme value to determine if it's a max or a min, you then perform the second derivative test. You evaluate the second partial of f, either with respect to x or y. The formula uses x, but you could also use y. And depending upon the sign of that value will tell you whether you have a local minimum or local maximum, respectively. All right? That is the second partials test. Now, I will tell you our example is rather simplistic. Those second partials were constant. They are not always constant. When we built our discriminant, because they were constant, our discriminant was constant. They're not always constant, so your discriminant is not always constant, folks. Sometimes you will prepare here most cases you'll prepare a function of x and y. Be prepared for that. All right? But for brevity in these notes, I went with this case. Now what we're going to come back to is another case where we're going to look at absolute extreme values on closed regions, folks. And that is going to finish our note set for this chapter. All right. But other than that, I hope you're hanging in there. And I'll see you in the next video. Catch you then.